In this lecture, we'll discuss another method for node embedding. In the last lecture, we discussed factorization based method where we use deterministic measures of node similarity like adjacency matrix or some higher order matrix to determine the node similarity. Weighted adjacency matrix was one of the examples we have taken. And we actually found out embedding which satisfies the embedding between two nodes u and v is approximately equal to some similarity metric between u and v. And we have learned this zu and zv as our embedding. Now we are going to look at the other class of methods called random walk based embeddings, where instead of using deterministic measures of non-similarity, we are trying to use stochastic measures of node similarity or probabilistic measure of node similarities. Here, as I told you, we are interested in, instead of having a deterministic quantity like adjacency matrix, we are trying to see if the probability of co-occurrence of the nodes in the network based on some short random walks in the graph. So we would like to figure it out, a connection between probability of co-occurrence of the nodes on the short random walks in the graph with the embedding of those nodes, which we are here looking at ZU transport ZV and some connection. So how can we do that is the question we are going to address in the next couple of minutes. So we'll start with a graph G with a V as a node set and E as a edge set, and we are assuming that it is a connected graph. Starting node U0 belongs to V, and we walk on this graph and we are at UT belongs to some node on the V. Now we have to determine what should be the t plus 1th node in the random walk. So we are at tth step of the random walk. We have started with the node U0, and now we have to determine what should be our next node. So how do we proceed with the random walk at the t plus 1th step is the question. So what we are going to do is, we are going to define probability of choosing the next node as follow. Here, given ut, I want to choose a next node which is ut plus 1, which I have defined as a 1 by degree of node ut if the ut plus 1 node belongs to the neighborhood of ut, otherwise is 0. So this particular set defines a neighbors of node ut. Remember, this is a connected graph with each node has a certain set of edges incidenting on them. So what this probability is, or what it tells us? It tells us that the next node should be selected from a uniform distribution randomly based on the current node and its neighbors. Remember that we are going to only look at the neighbors of ut, and we are going to randomly choose one node based on 1 by degree of this particular node at which we are right now as our probability. So this way we can actually keep choosing the node and can generate a random walk. Or we can look at this particular phenomena or process as a random walk generator, and we would like to know what is a random walk generator function. Random walk generator function will use this probability graph and starting node and the t. What is t? T is the length of my walk. How many steps I am going to take in that particular walk starting from u0. And the random walk generator will generate a set of nodes or sequences of nodes, if you want to think that way, starting from u0, and it will take t steps and provide us all the nodes which we have visited between u0 and the node at the t step. And what we will have, it will generate the set of nodes which we'll get at a after t step, not at t steps. Now we have a sequence of nodes and a random walk which is started from u0. What I can do is I can start for each node in V and get a neighbor sequence of nodes visited during the random walk. So I can keep repeating for different nodes in V for a length of t and generate a new random walks one after another one. So I can simulate m random walks of length t. The t can be of length 2, 3, 10 from each node. We can assume that each time the length t can be constant, or it can be a different size also. It is not going to change anything in terms of analysis. And we'll see why it will change. So now if I do this random walk for each node, then I have a total number of walks I have done is m cross n, m into n. For example, if I have n is equal to 10 nodes, which is a cardinality of my node set, and m is equal to 10, then at the end I have total 100 random walks each for each node of length t. Now let's see what is this set. So I am going to generate random walks of length t is equal to 2. It means that I will have 2 steps or 2 neighbors I am going to look for my node being a u, using the probability distribution which we have discussed earlier, which is uniform probability distribution over all the nodes in the neighbor of particular node. Okay. Now what I am going to do is I am going to, based on that, choose, and in this particular walk I have moved from u to x, x to w, and then I have x and w as my neighbors. So this is my set of neighbors in the first walk. Again, I am going to follow the same procedure. This time I have actually got v and w as my 2 neighbors, neighbor of u. Similarly, I have done for the third one, and I will get third neighbor which is x and v. And now what we are looking at is similarity of node based on the number of short path they have taken between them. Okay. So we have generated random walk of t is equal to 2, and I have 3 sets. One is, I can summarize here, n of ru First, for a first walk, it has xw. For second walk, it is vw, and the third walk, it is x and v. So I have m is equal to 3 here. I can repeat same procedure for z, y, x, v and w and generate more neighbor of each of these node, because I am starting from those node and generating their neighbors. Now the question is what we can do with these walks we have, or random walks we have. So now we know that how to generate the random walks, and we have those walks in terms of set of node visited, and now we have sequences of nodes visited during the each random walks. Now if you look at this sequence, we are interested in learning the embedding by predicting which nodes are in the neighborhood of U. And what we are going to do is we are going to take a little detour and try to borrow some ideas from the language models and connect our problem with the language model problem, which has been solved in the language natural language processing literature, and we will see how we can actually bring those solutions to our problem. So in the goal of language models is to determine probability of a sequence of the words. Take this particular sentence, the student made a detailed presentation is a valid sentence in the English language. It has all the element that should be there in a English sentence. Hence, if we are take this each of them as a set of words and a sequence of words, let's say W0, W1, U0, U1, U2, U3, U4 and U5, or W0, W1, W2, W3, W4, W5. Then we'll give higher probability to this sequence of words, because it makes sense when it comes to English language. Now look at this another sentence, made detailed the presentation student. When we give this sentence, native speaker cannot understand, or we cannot understand what is the message to be conveyed. It is not a valid sentence in the English language. And hence, if I want to give a probability associated with this sequence of words, I will give a low probability. Hence, we can see that there is a high probability sequence of words and there is a low probability sequence of word, and that makes a difference in their analysis. So, how to determine the probability of sequence of the words is the now question. If we find a high probability sequence of the words, then we can use that to say that this is a valid sentence. Otherwise, low probability sequence of the words, we will say it is not valid sentence. So now, what we are interested in is, given set of words W0 to Wn, the probability of sequence of words P should be found out using the data. And how can we find out? We can take data, use data, and see if we can capture the co-occurrence of this relationships between different words in the sentence or set of sentences or corpus. We examine them and try to find out the probability of different sequence of the words based on their co-occurrence. Now this is similar to what we are trying to do with nodes. And this problem has been discussed in the language model literatures, where what they try to do is find out the pair-wise probability of a word and the word next to it, or what they call it context. So I'm having a word and its context, and if I'm looking for that, what I'm trying to look at is that what is current word and what is the probability of having another next word, which is among all other words I have. So here what I can do is I can take this probability of a sequence of word, and under certain assumption I can write it as a product of probability of word given that the previous word. So it's a conditional probability that condition to what is the probability of wi, which is the next word, given wi minus one word. Let's look at this expression with the illustration of the student made a detailed presentation, where I'm looking for this sequence of words probability given the sentence. What I am going to do is I am going to decompose this particular probability into set of small probability, where I look at the word and the next word, which is context probability. So probability of students given the, probability of maid given student, probability of A given maid, probability of detailed given A, probability of presentation given detailed. And this particular probability, if I can find it out, I can get the probability of my sequence of words. So I have looked at the word and its context, which is the next sentence, next word, and try to determine the probability of a sequence of words. Of course, this is a simplistic model indeed, because we are only looking at a next context, contextual word. A neighbor is only a next one. We are not looking at the neighbor which is before it, the word before the current word, or even the words which are second next, third next, or previous second previous word or third previous word. So now can we do that? Okay, that is the one question. Another question we can also look at is, instead of predicting the context, instead of predicting the next word, can I try to predict the surrounding words from the context word? Let me explain this. For this example, the student made a detailed presentation. In this particular sentence, if I give you word made, can I predict the probability of surrounding word like the, student, a, detailed, and presentation? Is the question we can also ask. So instead of giving a given word, predicting the context, I am going to do other way around, trying to predict surrounding words based on the context word made. And it appears that in language, the skip-gram model does the same kind of task. What it does, it considers a context word, WC, and a size of window size of S. In other words, I will look, let's say, if I take a made as in my context word and look at the size window of 1, then I have these two, one word before made and afterward made. I want to predict if I take a size window of 2, I want to predict what are the words in a plus and minus 2 set. So S is the window size. And then what I am trying to do is, given the context word WC, I will like to predict a different word surrounding this context word in the window size of S. So I have a total 2 S context word I would like to predict. And what we want to do is, we want to maximize this probability for the getting a valid sequence of the words. Or from the data, I would like to find out this probability, maximize this probability. So how we can maximize this probability is the question we are going to answer. But already, as I told you, skip-gram model has done that. Why can't we use the parallel from the skip-gram model and get the probability which we are looking for in our random walk embedding? If you look at random walk is a set of nodes. If we look at our random walk and the language model, there is a similarity. You can think of random walk or each random walk as an artificial sentence where the node has a similar role as a word or set of words have in a valid sentence. So node can be think of as a words, and then we can try to use the skip-gram model where we are interested in, given a context node UI, what is the probability of a nearest or nearness of different nodes in a set of nodes in our graph, or what is the probability of co-occurrence of different nodes given the context node UI. So now it is a similar manner we are doing UI given UI. I want to predict what are the nodes in the nearness of my eye in some window size of S. And this particular parallel which we have earlier, where we are trying to predict words in the window size S given the context word, here we are trying to do the same, which is a neighborhood of UI. We are trying to predict what are the near nodes of UI. Or in a simple word, we are trying to predict the co-occurrence of different nodes in a neighborhood of UI. Of course, different random walks. And remember, our objective is not only predict this one, but also learn latent embedding function UFINC from V to R, or we would like to create a lookup table which allows us to gives us an embedding of each node in the graph. So we are actually interested not UI, but we are also interested in finding out this embedding function phi INC. So can we pose a problem of finding embedding using random walks as follow? We are interested in learning a latent embedding function FINC from V to RD for each node. It means we are interested in finding out some Z lookup table where when we apply FINC U, it will provide me embedding for the U of ZU of dimension D such that I maximize this particular objective function, which is log of probability of NRU given ZU. This is similar probability. If you look at it, the only difference here is instead of UI, we are going to use the ZU because we are interested in learning the latent embedding of UI. So now, how can we learn that is the question we are going to ask using the random walk. Sometimes we do not use only maximizations, often we use loss functions, so we have a negative minimization of this particular task. Remember that we want to learn using the data which we have actually generated through a set of random walks. Recall we have M cross N data. So we have this many random walks to actually determine ZU by minimizing this loss function. Let me summarize the random walk embedding. We want to simulate many random walks of the length t, 2, 3, 10 from each node u belongs to V. Once we have random walks, what we are interested in, for each node, we want to get neighborhood set as a sequence of nodes visited during the random walk. For each node u, we want to learn the embedding by predicting which nodes are in RU, or in other words, we would like to minimize this particular objective function sum over all the nodes in V. This can be decomposed into summation over V and all the V which are in the neighborhood of NRU. So this is basically for all the nodes, summation over all the nodes. This is the probability which will be approximated by certain methods like such as negative sampling or hierarchical softmax. We will discuss those methods in some time, and these are the summation over all the nodes in the neighborhood which are V for particular U. So we are going to keep doing it for each of the node in the V and their neighbors.